Okay, this is a problem from the last year 502 in class exam. This is a question number 2. Today we will try to solve this problem as my video project. Here we already know that X is a random sample from a Weibo to theta distribution. And here is a PDF and the expectation and the variance. Also, they remind us that pi is not a parameter but a constant pi. So for the first question, the number A, we are trying to find the best unbiased estimator of theta. So firstly, I will use the corollary 7.3.15 to solve this problem. So first step, we need to find the likelihood function, which is the joint of the PDF. Also xi has 2 higher than 0. And we can have the 2 power m c over pi theta n big pi of the xi and the e power the sum of xi square. Okay, same xi has 2 higher than 0. And the next step, we need to find the log likelihood function. We use natural log. Then we will have the log theta n times the log big pi xi times minus theta xi square. Then we will have n times ln 2 minus n times ln theta plus sum of the ln xi minus sum xi square divided by theta. And the next step is we're trying to get the derivative of this ln of the likelihood function. Because this is a constant and this is a constant to theta. So this one will be 0 and this one will be 0. And we only need to get the derivative from this one and this one. So what we have here is the minus n divided over theta plus the sum of the xi square divided by the theta square. And let's do a little bit of transform for it. We get a theta here and a theta here. And we add n here and n here. And then we take the theta square and n out. We will have the sum of the xi square divided by n minus that is the theta. And what we have here is, according to the corollary 7.3.15, this is a theta function, this is a wx function, this is another theta function. So according to the corollary 7.3.15, if we have a function like this, the variance of the wx attains the CRLB. So next step, we need confirm if the WX is an unbiased estimator of theta. So let's try to find the expectation of the, wait a moment, of this WX. That is equal then X. Because of IID, we have N times N E X squared. And the N disappeared. We have the E expectation of X squared. We know the expectation of X squared is equal to the variance of X plus the expectation of X squared outside. And we already know from the question, we already know the expectation of X and the variance of X. So we get into this, we get them into here. Wait a moment, let me make sure you guys can see it. Okay, so we have the 4 minus pi times theta divided by 4 plus the square, that is theta pi 4. And what we have here is the 4 theta pi theta plus theta pi, and this disappeared, and 4 cancel out. We have theta here. So luckily, the WX function is also an unbiased estimator for theta. So if we have this and this, which tell us the WX is an unbiased estimator for theta, and also the variance of the WX can attain the CRLB, which means the WX is the best unbiased estimator of theta, UMVUE of theta. And the WX is equal the sum of the xi squared divided by n. Okay, so we kind of finished the question A, but there's another way can do it. So let's try another way. We still stay with the question A. So firstly, let's check if this Weibull distribution belongs to the exponential family. Is it n here? Let's make this is a theta, 2 over theta times x, and the exp minus theta x squared. Is that correct? Yes. Okay, so here we have, this is our No, this is our c theta function. This is the hx. This is the w1 theta function. This is the t1 x function. So then, according to the SAM 6.2.22, we will find the complete sufficient statistic. That is the tx equal from the small t function. That is the sum of the xi square. And the next step, we have to check if this tx, the complete sufficient statistic, is unbiased. If this one is unbiased estimator, our problem solved. So we get the expectation of the tx equals e expectation of the sum xi square and we know because of the IID we get the n times the expectation of the x square, and the same as before, that's equal to variance x plus the expectation of x, the square outside, and we get the value in, which is from the question from the context. The variance is equal 4 minus pi times theta plus square 4 theta pi. And what we will have here is n theta. Oh, n theta. So, which means the tx is not unbiased estimator. But according to the theorem 7.3.23, we only need to do a small transformation of this and we can get the unbiased estimator. According to the theorem, if the tx is unbiased estimator of theta, then there is a function of the tx which is only based on t, will be the unique best estimator for the another function of theta. So then we need to find is what is the expectation of the t function, which is here, will equal the e t function divided by n, which will equal theta. So according to this, we know this is a new theta function, and this is our new function of t, because the t function is only based on t. So, and also it's unbiased. So then we know the t divided by n is the unique best meter for theta. And this is equal sum I xi squared divided by n. So which means we got the same answer as we use the corollary 7.3.15. Okay, let's come to the question B. Question B gives us a MME of theta and asks us to find an unbiased estimator of theta. So the first step is to check if this MME already unbiased. If it is, the question is tricking us. The problem solved. If it's not, we need to find out what is the bias. So, trying to find out the bias, we will try to find the expectation of the MME minus theta, which is equal the x bar square minus theta. This is a constant, so take it out. The x bar square and minus the expectation of theta. Because the theta is a parameter which is a constant, so the expectation of the theta is equal theta. And here the expectation of x bar square will equal the variance of x bar plus the expectation of x bar square outside minus theta. And there's some information we know before is the expectation of x bar equal expectation of x, which is equal square root theta pi divided by 2 in this case. And the variance of x bar will equal the variance x divided by n, which is equals 4 minus pi times theta divided 4n in this case. This is what we know before, and we put them into here to process. Here is the 4n, 4 minus pi plus 4 theta pi minus theta. Here we have the pi n and 4 theta minus pi theta, and here we have plus theta minus theta. Theta cancelled. We will left the 4 theta minus pi theta divided the pi n. Okay, so unfortunately, the MME is not unbiased estimator. It is a biased, and this is the bias. So the next step is we are trying to construct an unbiased estimator to cancel this bias. So if we, luckily is the bias is a constant, so if we directly cancel it by minus it, let's have a look at the expectation of this will equal this is a constant, so it will directly equal this. And here we have the, according to the process above, we know the expectation of the MME will equal 4 theta minus pi theta pi n plus theta minus this. So here they will equal theta. So then This is the unbiased estimator we constructed from the MME. Problem solved. Okay, the last one, number C. Number C is ask us to identify which of the two estimators, the answer for A and answer for B, has the smallest mean square error without doing any calculation. So what is the mean square error? The mean square error is equal the variance plus the square of the bias. So the answer for A is an unbiased estimator, and the answer for B also is an unbiased estimator. So we know the bias for answer A and B are equal 0. So if we are trying to find the smallest mean square error, which is kind of trying to find the smallest variance, this is our goal. Okay. The likely is when we do the question A, we use two methods. There is one method we use the corollary 7.3.15. We went through all this likelihood function, and when we come to here, we proved the variance of this estimator attains the CRLB, which is the smallest variance. So we can see because this estimator we got for the question A attains the CRLB, we know the variance for this estimator is the smallest variance. So then we can see this estimator has the smallest mean square error. So problem solved.